In previous class, I have discussed the calculation of magnetic field due to a straight current carrying wire using biot-savart law. Today, I will discuss the calculation of magnetic field due to a circular current carrying wire using biot-savart law. So, suppose this is a circular wire. This is a circular wire, and this is the center of this circular wire. The radius of this circular wire is suppose r. So r is radius of this circular wire, and current is I. Here is I is current. I is current. So if you want to calculate magnetic field at a point P at a distance d from the center of the circular wire, then this is the distance of this point P from the center of this circular wire. So using biot-savart law, you have to calculate the magnetic field at point P, and we have discussed earlier that when you want to use biot-savart law, you have to take a current element. What is the current element? IDL. So if I take a current element, here is DL in this direction. So the distance from this current element from this point P is suppose along this direction, this is x. So this distance is x along in this direction. So first of all, you have to find out the angle between the current element and this distance vector. So the angle between IDL, that means current element, and the distance vector x is how to calculate. Suppose this is a current carrying wire along this direction, and this is the axis of this point through this center. This is the axis, and suppose, and this is the distance. So this is the distance. So in this, here is the situation is in this way. So this is the center of this circular wire, and this is the axis of the circular wire, and this is you have take the ideal along this direction. Along this direction, this is a IDL. The direction of this DL is along this direction, and direction of this x is along this direction. The angle between DL and x is 90 degree. 90 degree. This angle will be 90 degree. So here is the angle between IDL and x is 90 degree. Here again I will tell you. Here this is the, suppose this is a circular loop. The direction of the current is along this direction. Okay. So if this is a center, then this pencil show the direction of this axis, and if you take this as a distance x, so the distance x and ideal is angle between distance x and ideal is 90 degree. That's why here I write that the angle between ideal and x vector is 90 degree. Now you have to apply biot-savart law. So the magnetic field due to current element IDL at point P is, suppose this is dB, so dB will be mu 0 I divided by 4 dl. Here is theta is 90 degree, so I dl sine 90 degree divided by x square. Here is x square. This is the distance, so it will be mu 0 I dl by x square, mu 0 I by 4 pi x square, 4 pi x square. This is the magnetic field due to this current carrying element IDL. Now if you take the theta angle is as a theta, then the direction of this magnetic field will be along this direction, perpendicular to this plane. So if I resonate this magnetic field into perpendicular direction, if this angle is theta, then this angle must be theta. This angle must be theta. So along this direction it will be dB cos theta, and along this direction it will be dB sin theta. If I take similar current element in this region, then it will be direction of the magnetic field will be along this direction. Suppose this is dB. If I resonate and this, suppose this angle is theta, then this angle will be theta. So along this direction it will be dB cos theta, and along this direction will be dB sin theta. Now you may ask how the magnetic field due to this current element IDL is along this direction. Why not in this direction? In lecture number 1 of this unit, I have discussed the similarity and dissimilarity between Coulomb's law and biot-savart law. And on this lecture, I have discussed one point. Suppose this is a rest charge, and this rest charge create electric field always radial. Suppose if you want to calculate electric field at any point, suppose this is R, so electric field must be equal to 1 by 4 pi epsilon naught q by r square, and the direction must be along this direction of R. That means it will be radial. But if you want to calculate the magnetic field due to the current carrying wire at a distance, suppose this is distance R, this is distance R vector at point P, what will be the direction of the magnetic field at P? This is current carrying, suppose DL, so this is the direction of DL. So direction of current element is always along the direction of current. So this is my right hand, so this is my right hand. I bend my fourth finger from DL to R. So this finger gives the direction of magnetic field. So here you see that the magnetic field is inward to this plane. So here you see that magnetic field is perpendicular to the IDL, that means current element, and also magnetic field is perpendicular to the distance R vector. So using this concept, here you see that the magnetic field due to this current element must be perpendicular to this distance. Here you see that The magnetic field must be perpendicular to the distance. So here is distance x. So this angle must be 90 degree. That's why the magnetic field due to this current element is along this direction, not along this direction. Okay. Now if so, you understand how magnetic field is along this direction, not along this direction. Now here you see that this component and this component is opposite and same in magnitude. So this component will cancel each other. So this component will cancel each other. But this component, both component is in same direction, in same magnitude. So the magnetic field due to whole circular wire will be equals to B dB sin theta. Okay, so this component will cancel each other, but this component is exists, so that's why it integration over this circle is dB sin theta. So it will be, here is dB is mu 0 I dl by 4 pi x square, and here is sin theta. If you put the value, this is theta and this is r, so this is x, so sin theta is r by x, so it is r by x, sin theta is r by x, so sin theta is r by x, and here is integration dl, here is integration, suppose this is integration. Now this is constant and this is constant, only dl is variable, so it will be mu 0 I by 4 pi x cube, it will be x cube, and here will be r and integration dl. So if you want to integrate over this circular path, then it will be 2 pi r. So magnetic field will be mu 0 I into r divided by 4 pi x cube, not x square cube, and here will be 2 pi r, because the integration over this circular path is the circumference of this radius, that means it will be 2 pi r. Now it will be, this is 2 to cancel out, then it will be pi cancel, that means mu 0 I r square by 2x cube, and here you see that the value of x is, here is r, here is d, then it will be r square plus d square, so it will be mu 0 I r square, and here will be, there is a root, so it will be x square plus d square 3 by 2. This is the formula of magnetic field at point P due to this circular loop. This is the equation. Now there are some special case, so you have to calculate the magnetic field on some special case. Here I have deduct the formula magnetic field due to current carrying loop on an axis at a distance r is mu 0 I r square by 2 x square plus d square 3 by 2. This is the formula. Now, number 1 condition. If you want to calculate magnetic field on a center, so magnetic field on the at the center of the loop. So if you want to calculate the magnetic field at the center of the loop, what will be the magnetic field? Here is the loop, at the center is R, this is the R. So here is D is 0, the distance, axial distance is 0. If you put this value, then it will be at center, it will be B0, B equals to mu 0 I R square divided by 2. This will be R square, not X square. This will be R square. This will be R square, not X square. This will be R square. Okay. So it will be R cube. So it will be mu 0 I by 2R, mu 0 I by 2R. Okay, magnetic field at a center of the loop. So this is condition number 1. So number 2. Number 2 is, suppose the magnetic field due to concentric circular loop. Magnetic field due to concentric circular loop. So suppose this is a loop, one loop, and there is another loop. The loop radius of the inner loop is R1 and radius of the larger loop is R2. The direction of current in same direction. So magnetic field due to current number 1, or that means loop number 1, B1, will be at center, it will be mu 0 I by 2 R1. But the direction is, here is my right hand. So right hand, it will be dl cross R. So this is the direction of dl and this is called R. So dl cross R. So it will be upward. Okay. And here is B2 will be mu 0 I by 2 R1. And this also upward. So total magnetic field will be B1 plus B2, because it's the same direction. That's why the vector will be same, only you have to add it. So it will be mu 0 I by 2, 1 by R1 plus 1 by R2. Now the condition number 3. What is the condition number 3? If the current is reverse, so suppose this is a loop, one loop of radius R1. The direction of current is along this direction, and another coincident loop is, suppose this is a radius R2. This is R2. The direction of current is along this direction. Same current but in opposite direction. So magnetic field due to this smaller loop, this is dl cross R will be along this direction. So magnetic field will be B1 will be along this direction. So it will be mu 0 I by 2 R1. And magnetic field due to loop number 2 is along this dl cross R, along this direction, dl cross R along this direction. So B2 will be this is upward, and P2 will be mu 0 I by 2 R2. This is downward. So total magnetic field will be B1 minus B2. So it will be mu 0 I by 2, 1 by R1 minus 1 by R2. It will be upward, because the magnetic field due to small circular loop is greater than the larger circular loop. This is the magnetic field due to the concentric circular loop. Now another is, suppose number 4. Suppose this is current, and this current is, this is loop. Then what will be the magnetic field at the point O? Magnetic field at point O. So here is, suppose this is I, then this will be I by 2 and this will be I by 2. So the magnetic field due to this upper section, it will be inward and this will be outward. So magnetic field due to upper, suppose this is A, B, C, and here is A, C, D. So magnetic field due to arc A, B, C will be, the direction will be, what will be the direction? Direction will be inward, and magnetic field due to A, D, C will be upward. But the magnitude on both condition is same. That's why the magnetic field due to this condition will be 0. Okay, magnetic field for this condition will be 0. Now if you want to calculate magnetic field, suppose this is number 4. Suppose this is a loop. Suppose this loop is along this direction current. This is R. This is R1. Then the magnetic field, this direction will be along this direction B1. And if you take the another loop, concentric loop, this is another loop, and current direction is along this direction. So it will be along this direction. This will be B2, and here the angle between is suppose theta. So magnetic field will be root over B1 square plus B2 square plus 2B1 B2 cos theta. This is in this way you can calculate magnetic field. Suppose this loop is perpendicular to each other. Suppose this is angle, and the magnetic field due to this loop will be B1. Suppose this is the R1, and suppose if you take another loop perpendicular to this loop, this is R2, the loop is R2, then the magnetic field will be, the direction is I, so magnetic field will be along this direction. This is angle 90 degree, so it will be, magnetic field will be root over B1 square plus B2 square. So in this way you can calculate magnetic field due to magnetic field using biot-savart